All right, wait for a few more people to join in. Let's get started. All right. So like I said right at the end, contactors again, coil, contacts, mechanical linkage. You're not going to be using replacement parts nowadays unless it's a very, very large contactor. Because you can have an industrial sized contactors can cost like thousands of dollars for a single contactor. So it's not unreasonable to buy parts for it, but it's not super common. As far as residential, you're just going to replace the whole thing. But understand you got three basic components. It's either the coil, the linkage in the middle, or the contacts on the end of it. That makes up the whole thing. The rest of it's just the plastic housing. All right. So relays are very closely related to a contactor. They are pretty much the same exact thing. They're a switch. They're an electronic, automatically controlled switch. What it's going to operate with is still, just like our other one we had, right under here. You can't see it as easily on this picture, but on the bottom of this contactor and the inside of this plastic casing, you're going to have an electronic coil. Now, that coil of wires is what we're going to use for a magnet to move a mechanical linkage inside of this housing. All right, so instead of being able to see the linkage like we would with a contactor, the relay typically is going to be completely sealed. These are ones that, even more than the contactor, you really can't replace components of it. You're just putting in a whole new relay. We're still testing the coil the same way as we would the other one. We're still going to be looking for either an open, a short, or a short to ground. We're going to check and make sure we're getting 24 volts into it. So on this contactor, for instance, we've got it where these four leads, these four connections on the bottom, those are going to be connected to your 24 volt coil. So you'd have power coming in on one side and then power going back to common on the other. And then you'd have it where, as far as your 24 volt connection, so 24 volt power, 24 volt common. And then coming in on this side, this has got two connections, so you could have 120 coming in on each leg, and then going out to, let's say, an inducer draft motor and a blower motor for a gas furnace or something like that. So relays, it's again still using the same concept, where we're going to have low voltage signal passing electricity automatically. The reason why we would use a relay over a contactor is space, really. That's the biggest one. Relays are much, much smaller. They can come in much smaller sizes. And nowadays, they have it where there are tons of relays in systems, but we're not going to see them as these replaceable parts. The relays nowadays are becoming part of the control board itself. So if you look at an HVAC control board, you're going to see on it nowadays, there's going to be these black little blocks on it. It's going to look like a black box that's going to be on these control boards. And basically, the whole, that little black box is a relay in itself. It's just a relay on a control board. It's part of that, that system. So as opposed to having another separate part or something like that, they put it in with the board. You'll have it where typically most systems nowadays, residentially at least, have one or two relays, depending on what kind of system they are. But for typical, just standard heat pump, like we have in the majority of Virginia households, it's going to be just a relay, just a single one relay. That's it. Maybe two. But they're, you know, it's the same idea we've got, where we're looking for 24 volts on our coil, making sure that our coil is good, make sure the power comes into the contactor, and make sure the power leaves the contactor. sorry, I'm saying contactor when I should be saying relay. Power coming into the relay, power's coming out of the relay. So either way, it's just us looking to see, okay, do we have confirmation that yes, there is power in and power out. That's all we're looking for a contactor or for a relay. Again, we've got it where there can be a number of different devices and styles. For the relay, you can see on this one a little bit, the bottom here where this coil is, there will typically also be a label, just like we had for our contactors. Our relays are also going to have ratings for voltages, for amperages, how much they can handle and everything. A relay, it's got two advantages to it. Well, it's got an advantage and a disadvantage. The advantage it has over a contactor is that it's smaller. The disadvantage it has over a contactor is it can't handle as large of a load. It can't handle as high of an amperage. A contactor can handle a much higher amperage, can handle much more of a load than a relay can, just because of how they're designed. So your relays are typically going to be seen for residential systems and even for commercial applications, powering something on like the blower motor or the blower fan, which is a very, very low amperage motor compared to the compressor and the condenser fan motor, which both draw in huge amounts of electricity in comparison. They draw in, that compressor is the main one. That, I mean, if you have it where you're trying to save a buck or something like that, and you're trying to pinch your pennies, and you know, you don't want to have you know, to spend a big bill on your electricity or anything like that, you don't turn the air conditioning on. That's the biggest trick. You know, you wait until you're sweating in your drawers 3 days in a row, and maybe we turn the AC on now. You know, you wait it out, and that's because that compressor, that outdoor unit, sucks up a ton of power and electricity. But an easy way to make it where you can maybe play it a little bit even longer is turning on the fan. Just on your thermostat, you can adjust it where instead of being the fan on auto, turn the fan to on, or turn the fan on some of them, you can turn it on circulate, where it'll cycle on every, 20, 30 minutes. It'll just, hey, let's move the air in the house, get it circulated, get it moving. And that can be enough to cool something down without requiring huge amounts of power. A blower fan requires very, very low energy compared to a compressor. So that's why blower motors, typically we're going to see relays. Compressors, we're typically going to see contactors. So again, like I said before, operation, application, construction, really much the same thing as a contactor. Coil contacts, and you got your line side, you got your load side. It's all pretty much the same exact thing. What it's used to control, though, like I said before, it's lighter loads. All right, so small things like fan motors or condenser fan motors or a damper motor. That's just something that literally is just opening and closing a damper inside of the ductwork. You'll see that for zone controlled systems, which you guys will learn about, as you go on with your through your classes and everything. And those dampers can actually, they're going to open and close ducts basically to make it so that, yes, we want air in the room. No, we don't. Depending on what the load is for it. So those are pretty good. Yeah, you'll see relays usually in series or combined with starting capacitors in what's called a kickstart kit, or just a kickstart. And basically, it's an easy way to fix an old system. So you got an old compressor, it's having a tough time starting up. Well, what you do is you get one of these kickstart kits that's a relay and a start capacitor combined together, and they kick on that start capacitor as needed to help that motor continue to run. And especially for compressor, it's going to help that compressor continue to run and start up a little bit easier. Typically, you're going to see that installed on units after they've been out there for 7, 8, 9 years. They're getting towards the end of their years. You put in a nice new start capacitor, and wow, this thing starts running just like it used to. And it's because you're giving it that extra juice. But the relay allows for that connection and disconnecting of that start capacitor, allowing it so that we only have the start capacitor engaging our motor when we need it to. Otherwise, we're getting way too much power to it and we'll actually burn out a motor. So it's a really great way for a starting capacitor to be used. Now, I recommend it typically for a customer. If it's part of the budget, you can figure it out, definitely do it. Cheaper units will typically not have a start capacitor on them. It's usually your high-end brands like Trane, Carrier, Lennox, those name brand ones. They're the ones that are going to say, hey, we're going to put a run and a start capacitor on our compressor, the heart of the unit. You know, we're going to try and make sure that that thing has all the power necessary for it. It's got all the components to allow it to start up and run efficiently. But for cheaper stuff like Goodman's, Amana's, what you guys have typically seen in the lab, basically, that stuff has got it where it's much, much, much cheaper. And because of that, why do I need to include this extra $100 $150 worth of parts? I don't need that. So I've seen it a lot of times. A lot of companies will do it where, as part of the install team, they'll tell the install team, hey, we sold this unit, install a kickstart with it as well. Don't just install it like it was from the factory. Install this extra part, and then we'll get the unit started. And the reason they do that, that kickstart with the start capacitor and the relay, is to make it so that that compressor lasts longer and that it has a better lifetime. Basically, right from the get-go, it's almost as if you could have it where from the beginning of a car operating from its first day, you had a way to make it where, you know, you could do, I don't know, I'm trying to think of a good comparison for a car. You had like an automatic battery change out after the first one dies, you know, it's automatically switched over, you know. That's kind of what this is like as far as, well, no, you know, it'd be more like if you had it where instead of one starting battery, you had two, you know. That's basically what this is going to do. So now instead of just having one battery to rely on or one capacitor to rely on to start up our big, powerful compressor motor, now we've got two, one for our start windings, one for our run windings, so that both can actually get energy as required. So that's the nice thing about that. But again, relays, we got a lot of different operations that we're going to see them used for. Control lockouts, again, I've talked about that a little bit as far as you're going to see that typically nowadays as part of a control board. You know, older style systems, you would see it where the lockout would also be part of the an actual relay control. It would be something with a temperature sensor or something sensitive to amperage. Typically temperature though, because that's the easiest thing to keep track of. So again, relays got a lot of different operations, applications, instructions, but typically it's like a contactor, just a smaller load. That's the whole idea behind it. All right, so the last thing we're going to go over, well, one of the last things we'll go over tonight is going to be overloads. An overload is a safety in a system. Its whole idea is to basically protect a system from too much amperage or too much power rushing into the system. If a high enough level of amperage rushes through a system and a wire is not rated for that level of amperage, the wire will catch on fire. All right, that's the big thing we try to avoid. All right, if I can avoid electrical fires, I'm thinking I'm doing a pretty good job as an HVAC technician. And that's my personal opinion, at least. But so these are there to make sure that we don't have where we're exceeding an excessive amount of amperage or temperature, because as a byproduct of electricity, always we're going to have it where we can have heat. heat is always going to be a byproduct. As electricity flows through our conductive wires, as it goes through everything, it's going to be creating a certain level of heat. If we increase that heat to a too high of a level, it will actually, like I said, cause a fire, will burn wires. It will, I mean, the thermoplastic around the wire will literally just melt off of it. You'll see it where you'll have burn marks inside of units. Wires will go from copper to charred black because they literally were just on fire, basically. They just burnt up. So we'll see that a lot of times that can happen with connections. To prevent that level of damage from going into our motors, we use an overload device. The most common one, number one out there, always is a fuse. Easiest, cheapest, it makes the most sense. It just works really, really well. You have it where it's simple construction, a conductor on one end, a conductor on the other end. In between is a thin piece of wire, basically, one that's going to carry just enough power through that, you know, and it'll be, and the just enough power is what that fuse is rated for. So if it's a 3 amp fuse, they're going to have a piece of conductive material in between those two ends that can carry 3 amps of electricity very, very well. Can it carry 3.5? No. When it gets to that 3.5, when it gets to 4 amps, typically it's going to be like a 10% thing, but it gets to 3.5 amps or something like that, it's going to be now, oh, that's too much amperage, and it will weaken that wire and that connection. Now, if it happens for a long enough time, depending on the type of fuse, it might be an immediate break. It might immediately disconnect and have it where you've got no power passing through now. Or it could be where you've got a slow blow fuse where it'll be, no, it'll let power pass through. It's fine. Let it go. And then it happens again, gets really high amp draw, and then fine, we're good. And then gets it one more time, but now it's been weakened those past 2 times, and now it breaks finally. Now our fuse actually disconnects. So the whole idea is just to make sure that we've got the amp draw of our components is not exceeding what they're rated for, or exceeding what our breaker panel is rated for, or our wires are rated for. We don't want to have it where we've got it where we go above, you know, anything like that. As soon as we start going extra amperage, as soon as we start exceeding and going to an excessive level, that's when we're going to start seeing system failure. And instead of that burnout happening in the fuse, it happens in the compressor, in the fan motor, on the control board. That's a really common spot because a lot of times nowadays, modern systems, there's going to be high voltage coming in, and it's going to go through a fuse, and then after that fuse, it goes into a board. And if that fuse didn't work right, or if it was too large of a fuse, someone puts in, you know, should be 30 amp, they put in a 50 amp, and it lets way too much power pass through, that can burn up and eat up a board instantly. And I mean instant. It doesn't take long for a board to be eaten up by too much power. It takes seconds. So as soon as it happens, it's done. Board's fried. Get a new one. So we use a fuse to protect all these different things. There's different styles of them that you're going to see. If you go old school back in the day, you're going to see the screw-in glass style fuses that you know, you might have seen in an old breaker panel or something like that, in an old house or a garage or shed or something like that. That's pretty common, but nowadays it's typically you're going to see two common types of fuses you run into. We've got our large and small brass fuses that are used in outdoor disconnects and indoor disconnects a lot of times. And then we've got our blade fuses. Blade fuses are going to be another one that's really common. You may have seen them before if you have ever done any automotive work. If you Google blade fuse, it's 2 little pegs, and a little plastic cap, and it looks like a Z shape. But the main thing on those is the rating. It'll be right on the top of it. It'll have a number. For us, typically it's going to be either 3 amp or 5 amp, and that's it. For automotive, you'll see them go up to 50 and 40 and 20 amp and everything. But for us, we're usually doing 3 and 5. Replacing those little fuses is annoying. All right, there's a tool they actually have where you can plug it in place of that fuse, and then it'll reset, and it's a resettable fuse. So if you keep having a low voltage pop or a low voltage short or something like that, where too much amp draw is happening on your low voltage side, that's where this fuse is typically going to be used. You can just reset it as opposed to, oh, put another fuse in, put another fuse in, put another fuse in. Because after like 3 fuses, you're wasting money. You know, you're just pissing it down the drain. And no one wants to do that, especially when you're either you're working for someone and you're trying to show your value. You want to show that, hey, I can be a good return on investment basically for your company. And one of those ways is to keep your cost of parts for your truck down. So having a resettable fuse is a nice thing. The sad thing is it's only for our really small fuses we use that. We don't have one for like 50 amp fuses. But our 50 amp and 60 amp outdoor unit fuses, those are going to be those big brass cylinders we're going to see a lot of times. And they usually are not going to be that hard to diagnose any type of fuse, whether it's a brass fuse, whether it's a blade fuse. Simple. For you guys on your meters, for everybody, it's going to be, you go on, you turn that dial to ohms or omega, that omega symbol. And if you hit the select, there's a red select button, you hit that 3 times, that'll bring up a little symbol that looks like a speaker in your, in the bottom display part of your meter where the numbers are and everything. It'll show a little speaker in the bottom of it. If that's what shows up, you should be able to touch your 2 leads right to each other and get a nice beep. You should hear a beep sound. That beep is a continuity test, and this is what we use for fuses. We do a continuity test. We just make sure from the start of this fuse to the end of this fuse, we have a continuous path for electricity to flow. That's all we're trying to check for. If we have where I check a fuse and I hear the beep on continuity, good fuse. If I check it and I don't hear a beep, bad fuse. No good, need to get a new one, and they're cheap. That's the nice thing about it. So they're cheap, they're easy, they're reliable, and they protect our systems very, very well. The problem they have is what it says right there at the bottom of this. Do not provide adequate protection from inductive loads. So, excuse me. So again, 2 conductors, piece of wire. Usually it's going to be to protect, again, our components, our wires and everything like that, to make it so they're not getting extremely high amperage. When you get that high amperage, you're bringing in that temperature, you're bringing in a lot of potential for damage on a system while it's operating. So again, we've got where it's going to be, depending on what kind of system we're working with, fuses are going to be used pretty much on all of them. Now, the only other thing we've got right here is another type of overload. We've got our line break and our pilot duty overloads. So a line break, all right, we talked about it before, that we have on a contactor. You had 2 sides of it, right? We had power coming in from our power line, that's our line side, and we had our load side, or power going out to our different loads. Now, the line break overload breaks the power coming in from the power line to a motor. And it's going to sense, typically it's going to be looking for either amperage or temperature. That's going to be your 2 most common ones for that. It can be a bimetal disc that just sits right on the housing of the motor, and it's just going to read, okay, how hot is it inside of this motor? If it gets to a certain temperature, I'm going to warp out of shape, I'm going to disconnect power and shut the system off. And that's the nice thing about that, is you've got it where it can react quickly to a temperature change. If you have it where, let's say it's a blower motor, really common thing for a blower motor to get overloaded and overheated, because people, as much as they like to say they do a good job, most people do not do a great job of replacing their air filters. It's a very, very common thing, especially for apartment complexes. The companies for those, typically they're going to be, oh, why do we need to replace the air filters? You know, unless they've been doing it a long time. If they've been doing maintenance a long time, they understand. Replace the air filters. It's a lot cheaper than replacing a bunch of fan motors. Because what happens over time is you've got it where the that fan motor is going to be drawing higher and higher amperage. It's going to be drawing in higher and higher temperature. And then if it's not got a clean air coming in, if that filter's not catching anything, then it's going to start pulling stuff into it. It's going to start pulling in dust, debris, skin cells, all that nasty dander and hair and everything pretty much is going to get pulled in. And it's going to, well, I've got an electric motor, a bunch of coils of wire inside of it. That's a magnet. That dust and everything like that gets drawn to that magnet and sticks right onto that thing. I've seen entire motors caked on where literally you peel it back like it's a felt or fiberglass gasket almost of just dust and hair off of a motor. And then all of a sudden the motor starts running smoother, the motor starts running quieter. And the customer's like, what did you do? I'm like, I cleaned your motor. Like, that's what you needed. Your motor needed to be cleaned. Thank goodness, you know, if they have a line break overload or something like that, it's going to be able to shut that motor off before it's an issue. What I'm going to do is I'm going to get a call and they're going to say, well, the AC's coming on and then kicking off and then coming on and kicking off. And by the time I get out there, you know, the AC, well, now it's just not working at all. You know, it just seems to come on for a minute, but it never really gets anything cool. And what's happening is that blower fan is kicking on. It's overheating. As soon as it overheats, it shuts the blower fan off. When the blower fan's off, now the compressor is going to keep running. It's going to build up excess pressure on one side or the other of the compressor, pretty much. And then when it builds up that excess of pressure, it's going to open a pressure switch, disconnect power to our compressor, to our outdoor fan motor, and now the whole system just shuts down until pressure regulates or equalizes back to normal, or that blower fan cools off, or both, whichever one happens first. So it just depends on what kind of a system you've got and how it's set up, what safeties it will have involved with it. But typically, the more safeties, the more overloads in it, the more moolah that the unit's going to cost. Because each one of these is another part that can fail. It's another component. It's sort of like, you know, you look at like a Honda or something like that, or a Kia. You know, import car, very, very basic. You can get like the super basic model Nissans that have, you know, roll-up windows and everything. Well, it's nice because, cool, I don't have to worry about all these fancy parts and controls compared to if I was buying like a brand new top-of-the-line German, you know, Mercedes-Benz or BMW or something like that. They've got a lot more safeties and controls. The benefit of it is, though, they can probably know when something bad's going to happen to that motor faster than the other engines would. You know, that's what you typically would hope for. You know, and but the problem also arises. Well, now I'm also, because I'm adding more safety parts, I'm adding more parts that could possibly fail and break. So then now I'm going to be having it where I've got to take it to the shop more often to replace things that I never had to replace before, because my old car never had a temperature sensor or a pressure sensor or some sort of a new thermal overload device. That's crazy. And that's a lot of customers are getting that because they're going from, well, I had a unit from the 1990s or the early 2000s, and now I'm getting one of these new high energy efficient units, because our energy efficiency, most of the units have pretty much doubled since the past 20 years. And then they're, you know, now they're not aware of, if they're not told, at least on install or on the day of sale and everything, hey, this is a new unit that's going to require more maintenance. You're going to need to keep someone out here on a more regular basis. They're going to get upset pretty quickly because they're going to notice all of a sudden, well, I had that unit from 1998 till 2020, and I only had a repairman ever come out 5 times, and the 5th time it was dead. Now I've got it where I've had this unit for, you know, it'll be 3 years down the road, let's say, 3 years, and every summer I've had to call someone out to do something on it, and if they're not on contract, not understanding that like that is a benefit now more than ever, it makes it where it's difficult for these for these people, because they're not only, well, now I've got this new energy efficient unit, but it seems like it's costing me more because I'm getting more and more repairs done. So it just depends. Everything as far as like I said, what the manufacturer does and what the customer wants, and everything. But educating them, like I've said before, it's one of those big things that can really help build that relationship. Because at the end of the day, you are out of that job, and you don't have a job because you know HVAC, because you know how to fix a unit, because you know how to use a meter, because you know how to replace a capacitor. Nope. You've got a job, and the reason your company's around and the reason you're doing work is because a customer called you out to take care of an HVAC system. The customer is always the reason why you're on the job. They may not always be right, but they're always the reason why you're on the job. That's the main thing. So educating them can always be a benefit for you and for that customer. Pilot duty overloads, again, we've got a couple different styles of them. Current, which is just amperage. So again, like a fuse, it's looking at amp draw to determine whether or not a system needs to be disconnected from its power source. Magnetic overloads, which are going to be reacting to the magnetic field. That's related to that current, all right? If I'm drawing in extremely high amperage to an electric coil for a motor, for a winding, that's going to increase the magnetic field of that winding. And if I increase that magnetic field, now my switch is going to see that, and it's actually going to react and will disconnect or connect, depending on what kind of thing we're looking at. But for a pilot duty overload, it's going to disconnect that winding and say, okay, yep, nope, don't need power anymore. We're good. We've got plenty of electricity. We've got plenty of magnetism. We're going to see these used a lot of times for something like our start windings for a compressor. To disconnect that power to make it so that now we just have the run winding energized, and the compressor, while it's running, now can consume less electricity than when it started. That's the thing. So on startup, a lot of motors will draw in, or all motors will draw in a huge amount of electricity, but it's dropping it down to a much lower level once it's running. That makes the system energy efficient. That's one of the big things, especially for older style systems. That was one of the big first moves that we had in the HVAC field, was to disconnect and control our windings and which ones were energized on startup and run. That led to a lot of energy efficient innovations. Nowadays, the last thing that's stated in here, electronic solid state overload. This is more of like your control board style stuff. And that's what we're seeing nowadays. Everything is pretty much switching to is control board style controls, where you've got something controlled by a board or a relay of some sort. And that's the whole way that it can actually operate and basically make the decisions of yes, turn on, disconnect, in what order, all that kind of stuff. It can adjust a lot of different things. So again, troubleshooting overloads, very simple. For fuses, it's just going to be looking, do we have continuity? For the other ones, we're going to be checking to see, they're typically going to be in series, all right? So when we have multiple things in series with each other, if one thing in that lineup goes out, let's say we had 6 light bulbs in series, one light bulb goes out, all the light bulbs go out. One light bulb gets removed, all the light bulbs go out. All right, so for our overloads, what we're going to see is, we're going to have from on this side, we'll have our compressor. On this side, we've got our power line from our breaker, all right? And it's going to take its path. It's going to start with the breaker, and then it's going to go into a disconnect panel. And from the disconnect panel, it's going to go into our overload, or into our contactor, into an overload device, and then into our compressor, all right? All along that path, we're looking to see, do we have power? Right at the breaker panel, do I have power? Yes or no. That's all you're answering. And then from the breaker panel, where is the next step it's going to go? Do I have voltage there? Yes or no. If along that way you can finally answer, no, I do not have voltage, or I've lost voltage leaving or coming into it, that's where you're going to see your problem. For an overload device, you're checking to make sure, yes, voltage is coming in, yes, voltage is going out. The problem one and the problem child for most of these is the internal overload on a compressor. This is one that trips up a lot of guys when they start out. It trips up a lot of people when they get out in the field, because it's something you can't see. You're not going to know if that compressor's got an internal overload. You just have to assume that it does, unless you check the wiring diagram and they happen to have it listed in that diagram. Then you might know for sure, yes, it has some form of internal overload. So what the internal overload on compressor does is it allows for the compressor to run, and then if it overheats or draws too high of an amperage, it's pretty much going to disconnect the power from our windings on the inside of the compressor. So, excuse me, too much ginger ale. The disconnect of the power is going to make it where that you have the compressor shut off. What it's going to look like, though, is you'll go to a unit, turn the power off, it'll be running, you turn the power off, you disconnect the leads from your compressor, and then you're going to check your windings on your compressor with your meter. And you're going to check on resistance. What it's going to look like when an internal overload on a compressor has been activated is it will look like an open winding. And guys will often misdiagnose and say, yes, I've got an open winding on this compressor. This is the issue with it. I'm going to get a new compressor in here. Because if you find an open winding on a compressor, if any of y'all find that, that means that compressor's done. It's at the end of that. Somewhere in the wires inside of that compressor, 2 wires disconnected. As soon as 2 of them disconnected, that's it. That's the end of it. No longer getting power to it. Got to get a new compressor. So you go, you take out the old compressor, you put in a new one, and it starts up right away. See, I knew it was just that, I just knew it was a bad compressor or whatever, and hope to goodness gracious it wasn't under warranty, because if that thing's under warranty, you got to send that compressor that you said was bad back to the factory, and they get to test it there. And if they test it there and they say, well, hold on, there's no open. Actually, this compressor is working just fine. You sure you didn't misdiagnose the internal overload? And you're like, wait, what? And they're like, yeah, by the way, we're not going to pay for that compressor that you just bought from us. You're not getting that for free. You owe us money now. Because that's what happens. And then and if that happens again and again and again, the boss starts saying, okay, well, now your butt's on the line for it, kind of thing. If it happens once in a while, they understand. It's an extremely common error for people to make. But it's one of those things you got to make sure. Now, how do you make sure that internal overload is not the issue? Let the compressor cool off. Give it 5-10 minutes. Honestly, that's all you got to do. Give a compressor 5 or 10 minutes. Make sure it's cool. Usually, by the time for residential systems, the amount of time it takes you to disconnect the power and to remove the outer shell of all the cover and everything like that from the outdoor unit, to remove the fan motor, to get down to the actual compressor itself, that'll give you enough time. If you're worried that the compressor is still too hot, you always can check the top of a compressor to see if it's been running recently, and that will let you know if it's hot. Just touch it. I always do it back of my hand, tap the top of it, and you'll feel it's hot, and you want to pull that hand right up. If it's still hot where you put your hand on it, it's whoa, like for a quick second, and it's too hot, you pull your hand back, give it some more time. Until you get to the point where you can just stick your hand on it and it's not going to burn your hand or anything like that, it's still too warm. So just give it time, let it cool off. An internal overload, now, if that's happening, my compressor's not cooling off, I'm going to start looking at some other things. I'm going to look at airflow. I'm going to make sure that I've got it where it's breathing properly. I'm going to make sure that I've got enough refrigerant. That's the only thing that's actually going to cool off that compressor. All right, we've got one last session that's going to start at 9 o'clock. we'll get started then and have everything ready to go, guys.
It is out.